I was just interrupted again by the computer, the program locking up. Trying to write CDs and capture video at the same time is apparently putting a strain on the computer, so that might happen occasionally. But again, we see that at the focal distance, moving the laser back and forth, keeping it parallel, doesn't have an effect. Out here we get retrograde motion, and in close we get parallel motion. Okay, now for a thin lens of this nature, the lens that we just saw has this shape. We have the spherical surface here and then the straight back, so this is a half convex lens. All the rays, all the parallel rays, for a well-made thin lens, and remember this is a spherical lens, we stay pretty, our deflection for this lens stays pretty small compared to the radius, just because the lens itself is pretty small compared to the radius. The radius of this lens, I think, is 4 inches, and that lens is only about 1 inch. So that the maximum deflection we could get from the center line would be 1/2 inch, or about 1/8 of the radius. So that all parallel rays will focus here. Now, for a well-made thin lens, see, lenses aren't always spherical. We correct for the fact that when we get far away from the center, the rays don't quite converge to the focal point. Okay, when we grind a lens, when a lens is manufactured, we work out mathematically exactly what the shape should be. It's going to be close to spherical, but it's not going to be exactly spherical. The lenses you have to work with are spherical. But well-made lenses that give you really sharp images and really sharp focus are less so. The point at which all the rays converge is called the focal distance. Now for a thin lens, okay, the difference between a thin lens and a thick lens is that in a thin lens, it's a lot thinner than a thick lens. That should be no surprise. The main idea of a thin lens is that the beam isn't significantly displaced going through the lens. Now this is actually drawn fairly thick, and we do have a significant displacement the way I've drawn it. And I'm not sure I've got the refraction here going in the right direction again. I'm not going to worry about that right now. But you see that the parallel ray comes in here, and it is displaced a little bit over here when it comes out of the lens. It's moved perpendicular to its original direction. So the beam starts out here, and then it gets moved over to here before it gets focused. Okay, for a thin lens, that distance is regarded as insignificant. For a thick lens, for the cylindrical or spherical lenses, of course, that displacement is real significant. Okay, in a thin lens, we neglect this displacement. We make the lenses thin enough that that displacement of the beam is not significant. Okay, so more generally, we usually draw convex lenses double convex. Parallel rays will come in and focus at a focal distance, and the focal distance is measured from the center of a double lens, like this. Again, this displacement here is regarded as being insignificant. I'm going to risk moving just a little further here. I'm afraid the camera's going to lock up, or the program's going to lock up. The camera's functioning fine. Let's say now that we've got a honey lens and we've got an object over here. Okay? We want to know what happens to the light that gets scattered off of the top of this object's head. Okay, there's light in the room, or let's say we're illuminating this object, this person. Of course, that's a pretty big lens, but this is kind of a symbolic picture. So we illuminate the top of this person's head at least, so rays of light come off of this person's head in all directions. Some of those rays hit the lens, here, 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 here. Okay? They all move straight from the person's head to the point at which they strike the lens. We want to know how we might get all those rays to converge in a point. Let's assume this person has a point on the top of their head, and we want the image of that point at some point on the other side of the lens. Now, one of the beams that comes from the top of the head comes in parallel to the lens and therefore is refracted back toward the focus and actually passes through the focal point of the lens. Another beam comes through the center of the lens and comes through undeflected. Okay, if we hit the center of the lens, we're going to bend a little bit here and we're going to bend back a little bit here. If it's a thin lens, the beam essentially continues along a straight line, undeflected, through the center. Now, if this person is further from the lens than the focal distance, and its picture's not really drawn that way, the person looks too close, so let's just assume though that the person is further than the focal distance, it's going to follow that these rays will get closer and closer together on this side of the lens, and they'll eventually converge out here someplace, way out here. They're not getting close together very fast, but they will eventually converge, provided this person's outside the focal distance. Let's talk about that just a little. If the person is right at the focal distance, which is about where the person looks, then the ray through the center will end up, just looking at the similar triangles here and here, this ray will end up being parallel to this ray, and they'll never converge. Okay? Of course, you've seen what happens if we put a lens at that focal distance. Okay, here we go. Now, let's see if I can keep it here. Okay, the F is getting bigger and bigger and bigger, and now it's really big, and there it just kind of blurs away. That's where we're at the focal distance, and then it turns upside down, as you just saw, as we pass the focal distance. At the focal distance, that F is infinitely large, which is why we can't make out the F anymore. Okay, the image really converges at infinity. If we move inside the focal length, these rays diverge, and we get this virtual image on the other side, and we'll talk about that eventually. Now, the big point here is that all the other rays that go through this lens will also converge at whatever point these two rays converge at. Okay? So all the light that comes from the top of this person's head that happens to strike the lens will all be focused to a single point down here, and you'll get the image of the point on the person's head. The same thing would happen to a point on the person's arm, assuming that the point on the arm was at the same distance from the lens as the point on the head. Okay, those rays would come through and converge at a slightly different point, but at the same distance behind the lens. And all the light scattered off of this person, it turns out, assuming that the whole person is all at an equal distance from the lens, will be converged at the same distance behind the lens. So we'll have this image of the person forming on the other side of the lens, and we'll talk about that a little bit more in the next clip.